Okay, we're now live on YouTube. So we're just letting people in. Magandang umaga po sa mga participants po natin dito sa Zoom. We just started our live stream on YouTube and we're just letting people in before we start. I hope yung yung audio ko is okay lang. Can you tell me otherwise?
Clear, Kuya G.
Okay, thank you. Thank you, Sir Chester. Glad you're here. Ayun po. So I think we can start already. Good morning to our participants here on YouTube and on the Zoom, of course. And Happy New Year. It's a brand new year for PhilSci Hub. And what a way to start this year is to start with a very informative and talaga naman pong tatak UPLB na webinar, and we are joined here today by Dr. Karen Laserna, one of our team members, one of the core team members of Filipino Science Hub, and she's going to talk about liquid chromatography for natural products research. So, ayan, we're very excited and about this topic, and excited na po kami to start this year with this very informative topic. Okay? And before that, I would just like to share the screen. Okay, wait a sec. Ayan. So again, this is PhilSci Hub, and we're on to the fifth installment of the DLSU and PhilSci Hub collaboration on modern analytical methods. And today, our topic is liquid chromatography, instrumentation and application in natural products research. And as I said, this will be delivered by Dr. Karen Laserna of the Central Instrumentation Facility of the Salle University. And well, they've been our partners since last year. And to talk more about the facility, this DLSU CIF is one of their core members, Dr. Virgilio Ebajo. I hope he's already in the room. Hello, sir. Sir Vir, are you there?
Yes, I'm here.
Okay, so I will let you share your screen.
Okay.
I'll stop sharing for a while. So, good morning po, sir. Kumusta po?
Good morning. I'll share my screen now.
Okay.
Okay.
Okay. Well set.
Okay, I hope my screen is visible now.
Yeah, totally, sir. Absolutely po.
Hi. So good morning, everyone. Good morning to all the audiences here in the today's PSI Hub webinar. I am Virgilio Ebajo Jr., the equipment specialist for the Central Instrumentation Facility of De La Salle University. So I'm here to give you a brief introduction of our facility. So the DLSU Central Instrumentation Facility is under the Office of the Vice Chancellor for Research and Innovation. And we house a diverse range of advanced analytical instruments. And we are located at the Binyan, Laguna, at the Laguna campus of De La Salle University. And we are located at the George SKP Advanced Instrumentation Building. And we also have a laboratory at the Richard Lee Engineering and Technology Block at the DLSU Laguna campus. So we are not only serving DLSU students and researchers, but we also serve the needs of our fellow Filipino researchers. In fact, we have clients from NCR, from North, from Luzon, Visayas, and we also have clients from Mindanao. So we offer the following services. So we can do analysis of your samples for your research needs. We also perform training if you want to learn how to use some of our advanced instruments. We can also do consultation if in case you need help on how to improve your research proposals or your results using our instruments. We can also offer a collaboration when, in case you do not know how to use your results and you want to maximize the potential of the results that you get from our facility. And we can also do research outsourcing. Now, our facility houses the following laboratory. We have the first, the NMR lab. So I am the one in charge of the NMR lab, and we have a 600 megahertz NMR spectrometer with capable of analyzing samples in solution and in solid state. So it is at present the strongest NMR instrument in the country and also the most advanced. We also have the spectroscopy lab, and this is handled by Chris Argamino. And we have in the spectroscopy lab, we have the UVVs with reflectance, FTIR with APR, particle size, and CTAP potential analyzer, ICP-MS, and elemental analyzer. Now, if you want to learn more about the application of spectroscopy for your researches, you can watch the previous PhilSci Hub webinar conducted by, I think, Chris Argamino. Now, we also have the chromatography laboratory, and in this lab, we have the QTOF LCMS, analytical HPLC, preparative HPLC with fraction collector, DCMS with headspace and autosampler. And this laboratory is handled by Ana Karen Laserna. So you are going to hear from her today, and I hope you pay attention for you to appreciate what these instruments can do and how it can help your research. We also have the Integrated Electron Microscopy Lab, which houses the Field Emission Scanning Electron Microscope with EDS, TEM, and also Focus Ion Beam. Now, if you want to learn more about these instruments, you can visit the previous PSI Hub webinar on electron microscopy delivered by Dr. Jose Esmiria, which is our equipment specialist for this laboratory. Now, we also have the Imaging and Cell Culture Lab. And in this laboratory, we have the confocal scanning laser microscope with live cell imaging. And this is handled by Sir Michael. And if you want to learn more about this instrument, you can also visit another PhilSci Hub webinar. So halos lahat nito na discuss na namin with PhilSci Hub on their previous webinars. Now, I also have a wind tunnel and testing lab. And in this lab, we have an Eiffel type wind tunnel equipment. And this is very useful for engineering researchers. Now, aside from those advanced analytical instruments, we also have the following instruments and equipments that we can share with you if you want to work or collaborate with us. So we have the freeze dryer, rotary evaporators, hot plates, ovens, freezers, refrigerators, dry boxes, switch meters, microcentrifuge, fluorescence microscope, cytogenetics workstation, cell culture facilities for mammalian, plant, and microbial cells, ultramicrotome, micromanipulator, gold and palladium spatter, analytical and semi-micro balances, and a water purification system. Now, we welcome this collaboration with the PhilSci Hub team, and we hope that with this collaboration, with the series of webinars, we can help motivate our young researchers and our future researchers who are still in their undergrad and graduate studies to use our modern instruments to their full potential. And if you are interested with collaborating with us or using our instrument, you can contact us through Facebook at facebook.com/DLSU CIF. You can also watch our previous webinars at our YouTube channel. You just search DLSU Central Instrumentation Facility on your YouTube search bar. And for inquiries on sample analysis, collaboration, and consultations, you may email us at cif@dlsu.edu.ph. So that's it. Thank you very much.
Sir, thank you. Thank you po, Sir Vir. So again po, yung Central Instrumentation Facility of De La Salle University caters not only to DLSU but for everyone who is interested to collaborate or use their services. So makikita po natin na talagang napaka-wide po ng range ng capabilities ng CIF-DLSU, and just contact them if you need anything, any analysis, kasi hindi lang po analytical chemistry, meron din silang mga for biotechnology na mga capabilities po. So just contact them through the contact addresses that they provided, and ayun po, patagal pa pong yung collaboration namin, and I hope that they will continue to support us at PhilSci Hub. So thank you very much, Sir Vir. I will move on to introduce our topic for today. Again, this webinar is all about liquid chromatography, instrumentation and application in natural products research. And our speaker for today is Dr. Ana Karen Laserna of De La Salle University CIF. And she's currently the academic service faculty and equipment specialist at CIF. And she's also a Balik Scientist awardee by the DOST, and she's hosted by the De La Salle University. She finished her bachelor's degree in chemistry, magna cum laude, at the University of the Philippines, Los Baños, and she has been a DOST SEI scholar from 2001 to 2005. Okay, so she also became the quality assurance specialist at Mead Johnson Nutrition Philippines, and she finished her PhD at the National University of Singapore in 2015. And her research mainly involved metabolomics of trauma injuries, and she has been a research fellow of NUS since then. Okay, so it is with pleasure that we introduce our speaker for today, Dr. Ana Karen Laserna, one of our core team members at Filipino Science Hub and a dear friend of ours.
Hello,
Dr.
good morning.
Karen, are you here?
Yes. Hello, JP.
I'm glad to have you back again. So ano po,
Suki na kami dito.
mainit-init pa ang aming offering for 2022.
Oh, suki na kami dito. So you can actually expect more from the DLSU CIF as well in the future. Hopefully, we will have more webinars also. Okay, so I'll begin our presentation, my presentation for today. Okay, so again, good morning to everyone. Thank you for joining us this Saturday morning and allowing me to share this presentation with you. So my talk today will be on liquid chromatography, instrumentation, and applications in natural products research. So we'll first go through a bit of the basics of chromatography and liquid chromatography, and then magpo-focus tayo dun sa instrumentation at saka yung applications in natural products research. So first, what is chromatography? So chromatography is actually an analytical technique wherein the components of a mixture are separated based on their partitioning or interactions between two mutually immiscible phases. And this is an important aspect. Dapat two mutually immiscible phases. So hindi dapat sila magmi-mix. So you would have these two mutually immiscible phases will consist of your stationary phase. So stationary, meaning fixed in place, either in a column or planar surface. You would also have your mobile phase that moves over or through the stationary phase, and it will be the one carrying your analytes or your compounds. So this technique is actually very popular. It is used worldwide in different laboratories, be it for research purposes or even for industrial purposes. It is used for quantitation, identification, as well as for purification purposes. So just to give a bit of background, so this is an example of paper chromatography. This is something that you can actually perform in your home. If you have dye or plant extracts, you can separate the components in a paper chromatography setup. So you would have your paper, for example, filter paper material or other paper materials, and then you just put at close to the bottom your extract or dye extract, and then you can just dip it in a solvent. So you would see subsequently that through the capillary action of the solvent through this paper, you will have the separation of your different components. And in this case, you would see like your initial extract being separated to different components that are colored. So you have those that are green in color, blue, red, orange, etc. So ito yung basic na concept behind chromatography. So you have a stationary phase, and your analytes, as they move through the stationary phase together with your mobile phase, will have these interactions or partitioning between these two phases. And that will cause for them to separate. Kasi iba-iba sila ng characteristics, iba-iba sila ng structure. They would have different affinities or interactions with the stationary phase, and that will cause their separations. So let's just have a brief overview of the history of chromatography. So the technique was first used in the late 1800s to early 1900s, and the first person to which the discovery of chromatography was actually attributed is Friedrich Ferdinand Runge. So he used paper to analyze dyes, probably something similar to what we have seen earlier. Ralph Lisigang was the one who first published work involving a technique with strong resemblance to modern paper chromatography. It would have something of a setup like this. But the invention of chromatography is mainly attributed to this guy, Mikhail Sveit, a Russian-Italian botanist. So what he did was he made use of a column that is packed with calcium carbonate to separate the plant pigments. So this is the first use of column chromatography. So he is also the one to first coin the term chromatography and correctly interpret the chromatographic process. So that's why the chromatography, the invention of chromatography, was mainly attributed to him. Modern chromatography is mainly attributed to these two guys, Arthur Martin and Richard Synge, who won the Nobel Prize in 1952 for their invention of partition chromatography and for their plate theory. So ano ba tong plate theory na to? So the plate theory or the theoretical plate model of chromatography is actually this is one of the core concepts behind chromatography. So in the plate theory or theoretical plate model, it supposes that the chromatographic column contains a large number of separate layers called theoretical plates. So this is a representation of your column. You have different layers of theoretical plates, all of the same sizes, and you have the separation of your analytes through the equilibrations of your analytes between the stationary and mobile phases, and these occur in your theoretical plates. So the analytes moves down the column by transfer of the equilibrated mobile phase from one plate to the next. So your analyte together with the mobile phase transfer across these theoretical plates, and in that process you have these equilibrations of your samples between the stationary and mobile phase. So but please take note that this is not what the column contains in real life. So this is mainly just a representation. So it is for the plates do not really exist. your columns mainly consists of like particles that are packed into the column. So it is just a measure of the, it's a way to measure the column efficiency. So you can do that by stating the number of theoretical plates, n. So the more plates, the better, or by stating the plate height. So the smaller the plate height, the better. So by examining a chromatographic peak, you can calculate the HETP is equals to the length of the column over n, where n can be calculated from your retention time as well as the peak width at half height. So this will be the formula. So again, in terms of like efficiency, if you have more theoretical plates, then you would have higher efficiency in terms of HETP or height equivalent to a theoretical plate. The smaller the HETP, the better. You also have the rate theory of chromatography. So this is actually, it explains the different mechanisms that are involved in band broadening. So you have this band Vandenter equation. So the HETP or the plate height can actually be calculated using this equation, A plus B over mu plus C mu, where mu is the average velocity of the mobile phase. A, B, and C are factors that contribute to band broadening. And these three factors that contribute to band broadening includes first, your eddy diffusion. So you can just imagine your analytes moving through the column, and you have a column that is packed with your stationary phase particles that are within this column. So as the analytes go through your column, at the start, they will be going through at the same time, but as they go through the column, you would expect them to take different routes. So random yung routes that they will be taking. And this will contribute to the band broadening. So some will take a shorter route. They will elute out first. Those that will next elute out first will be the majority of, or the bulk of your analytes, and they will be somewhere in the middle wherein you have the highest point of your peak, and some will be more retained due to a longer random path, and they will be eluting later. You also have your longitudinal diffusion, so B, your term B in the Vandenter equation. So analytes diffuses out from the center of the edges, from the center to the edges. So you can just imagine, again, at the start, they will be mainly like one plug, but as they travel through the column, you will see diffusion. Some will come out earlier. Majority or the bulk will again come out at a middle or at a median retention time, and you would have some that will be coming out later. So there is a diffusion of your analytes across as it moves across the column. So if the velocity of the mobile phase is high, then the analyte spends less time on the column. That decreases the effect of the longitudinal diffusion. The longer the time that it spends in the column, then you would expect the contribution of longitudinal diffusion to be more in terms of the band broadening. Now, in terms of resistance to mass transfer, you can just imagine your analytes equilibrating between your stationary phase as well as your mobile phase. Now, if the velocity of your mobile phase is high, then the analyte that has a strong affinity for the stationary phase will have a harder time to go into the mobile phase. So you will have the analytes in the mobile phase. So for example, you have one compound. Those that are in the mobile phase will come out earlier, and those that are in the stationary phase will have some resistance in going into the mobile phase for it to flow across the column. So this is your resistance to mass transfer. So the higher the velocity, in this case, the higher the velocity of the mobile phase, the worse the broadening becomes. So that is again because it will be harder for those that are in the stationary phase to go into the mobile phase. Now this is known as the Vandenter plot. So this is a representation of the relationship that is represented in the Vandenter equation. So it is a plot of plate height versus the average linear velocity of the mobile phase. And actually, the contributions coming from your longitudinal diffusion will be with lower at this point where you have higher, faster mobile phase velocity. Sorry. Okay. So the contribution coming from longitudinal diffusion will be at the start, whereas those that are coming from your resistance to mass transfer will be coming more at this part wherein you have higher velocity. Therefore, again, that's the part wherein the contribution coming from the resistance mass transfer will be higher. The contribution coming from your eddy diffusion will be it's pretty much regardless of whether it's not dependent on the mobile phase velocity, but rather a property. It depends on the properties of your column. In terms of the Vandenter plot, it is mainly contributions coming from your longitudinal diffusion as well as your resistance to mass transfer. Again, resistance to mass transfer occurs, the band broadening is higher if you have higher mobile phase velocity. Longitudinal diffusion, the contribution will be at the lower mobile phase velocity. So there are some important terms in chromatography. So you have the retention time. So this is the time between the sample injection and an analyte peak reaching the detector at the end of the column. So this is just a representation of your chromatogram. You have the detector signal as well as the time. So this is representative of the retention time, or the time that it takes for your components to elute out of the column and reach the detector. You also have your TM here. So this TM here is actually the time taken for the mobile phase to pass through the column. So this is so you can just imagine your mobile phase. It would not have any interaction or affinity towards your column. So it will elute out first before anything else. But sometimes you might have compounds in your samples that are also do not have any interactions or retention with the column. Then it will also elute together with your mobile phase. So you also have a term called retention factor, or K prime. It's often used to describe the migration rate of an analyte on a column. So it can also be called capacity factor. So the retention factor for an analyte is defined by this equation, using your retention time minus T sub m over T sub m. So when an analyte retention factor is less than 1, so the elution is fast. That accurate determination of the retention time is very difficult. So kailangan you would have to have a retention factor of greater than 1. So usually dapat greater than 1 yung retention factor mo. Kapag naman super taas yung retention factor mo, such as greater than 20, then the elution will take very long. Now you also have your selectivity factor. So this describes the separation of two species, A and B, on the column. So alpha can be calculated from your retention factor. So you can just have the retention factor from your species B and species A. So species B will be the more retained component, whereas your species A will be the less retained. So from there, you will calculate an alpha value that should always be greater than 1. So this is just a summary of what I have explained earlier. You would also have your partition coefficient or partition ratio. So this is something similar to your equilibrium constant expression. So you have an equilibrium constant expression between the based on the distribution of your analytes in the stationary and the mobile phase. So these can be represented by this formula. K is equals to the concentration of your analytes in the stationary phase over the concentration of your analytes in the mobile phase. You would also have your capacity or retention factor, again, This is the rate at which the analyte migrates through the column. It has to be greater than 1, but not so much that you have too much retention on your column. So this is given by this equation as well. You would also have your selectivity factor alpha. It is the ratio of the partition ratio of the more strongly retained to the partition ratio of the less strongly retained. So this will be the formula for this one. So there are different forms of the formula depending on what values or information is given. So you also have the number of theoretical plates. This one I have also discussed with the plate theory model. So this one is a measure of the separation efficiency of a column. So again, n is the number of theoretical plates given by this equation, or the equation that I have presented earlier, and this can be equal to the length over the height of the height equivalent of a theoretical plate. Okay, so you also have again resolution. There are different formulas. There are several formulas for which you can calculate resolution. So these are other formulas that you can use. This one is based on retention time as well as the peak width that have a height. And you would also have this form that is making use of the number of theoretical plates, the retention selectivity factor, as well as the retention factor. These are also some derivations of for the calculation of resolution. If you are looking at converting if you are able to calculate the resolution and number of theoretical plates for a particular column, and if you want to improve on that, you will be able to use this formula as to, for example, what would be a more suitable column given the resolution that you would want to achieve, or what would be a better number of theoretical plates, and what would be your expected retention time given a change in column. So those can be calculated using this formula. So these are more of like theoretical aspects of chromatography. Now we look at the different separation mechanisms that are employed in chromatography. So for this one, first you have adsorption chromatography. So you have a stationary phase, and then your mobile phase with the analytes will flow through the stationary phase, and your analytes or your solutes will adsorb on the surface of the stationary phase. So that is why it's called adsorption chromatography. You would also have partition chromatography. So partition meaning your components is partitioning between two immiscible phases that are, for example, liquid. So you would have, for example, your liquid mobile phase or gas mobile phase, and you are partitioning your analytes between that mobile phase as well as your stationary phase that is liquid embedded on a solid support. So an example of this would be in your gas chromatography setups. You would have your open tubular column. You have your mobile phase is gas. Your analytes are partitioning between your analytes are partitioning as it interacts with the solute. In the liquid that is present in the stationary support, which is your column. So that will be your partition chromatography. You also have molecular exclusion chromatography. So in this case, your separation is occurring based on size of your analytes. So you would have your stationary phase that is like a solid particles that has pores or pore networks, wherein your smaller molecules will enter through these pore or pore networks, and your large molecules will be excluded. So in that manner, your large molecules will elute out first, whereas your smaller molecules will penetrate in the pores and get retained and come out later. You also have your ion exchange chromatography. So this one, you have your stationary phase that is that has a covalently attached um, either cation or an ion, and then you would be able to separate the opposite charge of ion using that stationary phase. So for example, if you have um, ions that are attached to your stationary phase, and that will have a counter anion. So when your analyte goes through your stationary phase, these counter anions will be replaced by your analyte anions, and they will have this interaction with your stationary phase, and they will be retained. And subsequently, you can elute them out using a different mobile phase. So that is ion exchange chromatography. You also have an affinity chromatography. So this is useful for separating certain biomolecules of interest. So you would have ligands that are attached to your column. And this particular ligand will have a specific affinity for a certain type of compound. So it can be antibody to a certain protein or antigen, or other forms of ligand other forms of biomolecular interaction. So in terms of chromatographic techniques, actually you can summarize chromatography based on different parameters. So for example, if you summarize based on classify based on mechanism, you would have your partition chromatography, the one that I presented earlier, adsorption, ion exchange, as well as molecular exclusion chromatography. You can also classify them based on, you also have your affinity chromatography. You can also classify them based on the bed shape or the chromatographic bed shape. It can be planar. So planar in the case of like thin layer chromatography, paper chromatography, as well as electrochromatography. You would also have columnar chromatography or column chromatography. So this will be something that will be we're a bit more familiar with. So HPLC that is on column, as well as your GC. You also have classification based on the physical state of your mobile phase. So this will be, for example, gas chromatography. So gas is the mobile phase. Liquid chromatography, you have liquid as the mobile phase. And supercritical fluid chromatography, you have supercritical fluid as the mobile phase. So these are the different ways by which you can classify your chromatographic techniques. Okay. So far, okay pa? Okay, so with
So,
yes, may questions na? Wala
I
pa.
don't,
Okay. So, ngayon punta tayo sa liquid chromatography. This will be the focus of our talk today, particularly HPLC or high performance or high pressure liquid chromatography. But just the background, ano ba tong liquid chromatography? So as I've mentioned earlier, when we say liquid chromatography, your mobile phase will be liquid. So this one, the stationary phase can either be solid or liquid. So you can have liquid-liquid chromatography or liquid-solid chromatography. It can be in planar or columnar chromatographic bed. So we're familiar with these types of a more basic chromatography wherein you don't have so much instrumentation. So you have your column chromatography as well as your paper chromatography or thin layer chromatography. So basically you have a glass column, and then you would pack that with the stationary phase, and then you put your sample mixture on top of that column. And then as you add your mobile phase, and through gravity, the mobile phase will flow through the column. And with that, it will be bringing your different components through the column and separate them out based on the components retention to the stationary phase. And subsequently, you can collect them out as it reaches the bottom of the column. So this will be your column chromatography. Planar chromatography, this will be something similar to this. You have your samples that are paano ba sabihin? Parang you put small amounts of your sample at the end of your paper or thin layer plate, and then you would dip it in a certain solvent. It is usually enclosed para hindi rin nag-evaporate yung solvent mo, kasi usually you make use of organic solvents that are volatile. So you would want to close your setup so that you don't let the solvents evaporate. And with that, you will have capillary reaction moving your mobile phase through the paper or TLC plate, and that will allow the separation of your different analytes through as it gets retained in on your stationary phase. So yun, liquid chromatography, hindi lang siya based sa column chromatography. Actually, we also consider paper chromatography, thin layer chromatography, as well as electrochromatography as forms of LC. Now we have HPLC, so high performance liquid chromatography. In some cases, it's also referred to as high pressure liquid chromatography. So LC system, this is an LC system that makes use of small particle columns through which the mobile phase is pumped using high pressure. So that's why it's called HPLC high pressure liquid chromatography or HPLC high performance liquid chromatography. High performance kasi in the sense na coming from your column chromatography wherein ang nagmo-move lang ng mobile phase mo is gravity. Sometimes it will take very long for the components to elute out. And so they made use of like pumps to pump the mobile phase through the column at high pressure. Then you would have faster elution of your components. So this will be an example of a very early setup of LC. You have modular components that are homemade sa lab. So you would have different components of your HPLC. You have more integrated systems now coming from different instrument manufacturers. So this one will be a basic basic HPLC systems. And now you would also have your 2D LC. So 2D LC or two-dimensional LC will allow you to have two columns to separate out your components. So usually it can either be the same type of column chemistries, or it can also be different column chemistries that are complementary to each other, so that you'll be able to separate out your components more. Now, this one will be a bit more complicated in terms of configuration. In some cases, you might not need an extra pump, pero for more robust and more reproducible separations, you usually would employ a second pump and a certain number of diverter valves. So it can be that whatever is separated in one column subsequently will be directly separated in the other column, or there can be like a loop sample loop storage in between, so that you'll be able to collect each peak that is coming out from the first dimension and then separate them out in the second dimension. So that will be 2D LC. Now, there are different components of an HPLC. So you would have your solvent, your mobile phase. You would have a pump that manages the delivery of the solvent into your chromatography system. You would have an autosampler or injector that allows you to introduce your sample into the LC. And you would have the HPLC column where your chromatographic separation happens. So this HPLC column will contain your stationary phase packing material that will allow you to separate your compounds. After eluting from the column, your analytes and the mobile phase will go through the detector. And then subsequently, depending on the detector, it can either be a destructive detector wherein hindi mo na mariretrieve yung samples mo, or it can be a non-destructive detector that will allow you to either collect the samples for further use, or it will go to waste. So together with the detector, you will have connected a computer data system that will allow you to record the acquisition of your data. So it will record your chromatograms, showing you the separation of your different components. So again, those that are least retained will elute out first. Those that are retained more will elute out later. Okay, so in terms of the different modes of HPLC, so you have different modes of HPLC depending on the stationary phase and the mobile phase employed. One classification will be based on like what I have previously discussed based on mechanism. Another will be these few modes of that I'll be sharing now. So you have your normal phase LC. So in this case, it is a liquid solid chromatography or adsorption chromatography. So you would have your polar stationary phase, either silica or alumina, and the non-polar mobile phase. So example will be hexane. So that is commonly used for a normal phase LC. Your polar analytes gets retained more in the column because as you can imagine, your stationary phase has silica will have hydroxyl groups, and your polar compounds will be interacting with this hydroxyl groups of your silica, and therefore it will get retained. Those that are non-polar will not have interactions with this polar stationary phase, and then they will elute out first. Another and more commonly used mode of HPLC is reversed phase LC or RPLC. So in this case, you have partitioning of your analytes between the mobile phase and a non-polar hydrophobic stationary phase that is bonded on solid support. So previously, yung mga LC columns, partition chromatography, wherein you have your column containing this liquid that is embedded on the solid support. For example, beads, and then you would have like some solvent that is embedded on these beads, and nagkakaroon ng partition yung compounds mo between this mobile phase and the stationary phase that is embedded on that solid support. Subsequently, they have changed the stationary phase. So instead of having beads or particles into which your stationary phase liquid is embedded, they have covalently bonded certain chemical functional groups on the solid support that serves as a liquid-like layer. So kumbaga, instead of having that liquid that is bonded on your solid, you now have covalently bonded non-polar or hydrophobic groups on your column. So with this one, you have these non-polar hydrophobic groups bonded on the column. Your non-polar compounds will interact with this through hydrophobic interactions, and then your polar compounds will elute out first. So actually, reverse phase LC is the most commonly used mode of HPLC, be it for natural products or even for other forms of applications. Now you also have, as discussed earlier, ion exchange chromatography. It is basically ion exchange chromatography mainly exists in HPLC mode. So you have your ion exchange resins, you would have interaction, you have your counter ions, and then you have your analytes that interact with the ionic groups that are attached to your silica support or polymeric support, and that will allow the retention of these positively charged or ionic analytes into the column. Also, HPLC, you would have your size exclusion chromatography, or earlier, as I mentioned, molecular exclusion chromatography. This is mainly used for the analysis of polymers. So it can be synthetic polymers or even biopolymers. And this allows you to separate out based on the size of your compounds. Other modes and related techniques would be, again, affinity chromatography. This will involve receptor ligand interactions. It will be specific separation or retention will be specific to the molecules that has interactions with the immobilized ligands. You have chiral chromatography to separate chiral molecules, separation of enantiomers. Now, one thing to note when you want to do normal phase LC, not all LC instruments are suitable for normal phase LC. So that has to be taken note of. One is because you are using highly flammable solvents. Some LC instruments might not be spark proof. So pwedeng cause of fire yon. And secondly, you might have materials that are in the LC system that is not suitable for your LC system. So, that are not suitable with the solvent that is used for normal phase LC. And so, if you're going to purchase an LC instrument, you would need to take note of that if you want to do both reverse phase and normal phase LC. So, paano naman kung ang LC mo is definitely for reverse phase lang? So, medyo stuck ka na, di ba? Hindi ka makakapag normal phase kasi yung mga gamit that are in your instrument might be more suitable for reverse phase LC. Now, you can have certain modifications to the system. You can change some of the parts or materials, pero medyo mahirap din siya because you don't want also to like keep on changing materials or parts in your LC system. So, another option to separate out your polar molecules will be this hydrophilic interaction chromatography. So this is a bit, it is a technique that is a bit newer. It is highly orthogonal to your reverse phase LC. It allows you to separate your highly polar analytes. So the way it works is that you have your stationary phase, and then you have functional groups that are attached to your stationary phase that allows the retention of water. So yung components mo will actually be separating or partitioning, or the separation will occur based on partitioning of your compounds between the mobile phase and the water layer of your stationary phase. So ganon yung means of separation of hydrophilic interaction chromatography. So you have a water layer wherein the partitioning occurs. Now, in most cases, your helic functional group will also have charges. So in addition to the hydrophilic partitioning, you would also have electrostatic or ionic interactions between your analyte and the functional group in your stationary phase. So it is a must that you have at least 2.5% water in your mobile phase for this helic interaction to occur. Of course, kasi nga yun, kailangan mo ng water dun sa stationary phase. And the good thing is it makes use of the same reverse phase solvent. So for example, in reverse phase, we usually use water and methanol and acetonitrile. You can use the same solvents for hydrophilic interaction. You just need to change the composition. So for reverse phase LC, you would usually create an elution program, which we will talk about a bit more later, wherein you start with low organic to high organic. Kapag hydrophilic interaction chromatography, you make use of high organic to low organic. So it is very complementary and orthogonal to reverse phase LC. Now, you also have hydrophobic interaction chromatography. This is analogous to RPLC, except that it uses mobile phase of low organic content and high salt concentration. So we have proteins. They denature fast in the organic solvents that are used in reverse phase LC. And so for us to separate them out, then it will be better to use hydrophobic interaction chromatography, wherein you can employ buffers or high salt concentration solutions. You also have electrochromatography. This is something that is it employs chromatographic mechanism, but it makes use of a CE equipment. But you have a packed capillary column. Supercritical fluid, it's related. It makes use of similar HPLC packed type of columns, but instead of liquid for mobile phase, it makes use of pressurized supercritical fluid. So this is for nonpolar analytes and chiral molecules. Okay, so I've mentioned earlier that an important aspect in chromatography is to separate out your components, diba? There's no use if you cannot separate out your components. So separation of components, again, is measured by this parameter resolution. So it's a measure of the efficiency or the separation efficiency of your chromatography. Now, for good separation, you should have resolutions that are greater than 1.5. And there are three factors that influence resolution. So from the equation that we have earlier, you have selectivity, efficiency, and retention. So efficiency represented by the number of theoretical plates, selectivity by this term here, and retention by the retention factor term here. Now you can see that in order to increase the resolution, you can actually increase N. So you increase column length or use more efficient columns. You can also choose to increase the retention of the analytes, increase the K term here, or increase selectivity or alpha. So you make use of a more selective column or mobile phase. So as you can see from here, to increase your resolution, you actually have the highest increase in resolution if you change the alpha, yung selectivity factor mo. So this, again, will be coming from changes in your column and mobile phase. So here is just to illustrate that you have most contribution in improving resolution using alpha. So with increase, with the initial, you have not overlap peaks. By increasing your retention factor, you can separate them out. Increasing alpha, better separation. Increasing N, slightly overlap pa. So as mentioned, you can increase the alpha or selectivity by depending on the columns that you use. So let's just go through the considerations in terms of column selection. So you can change column chemistry depending on your polar analytes of interest. These are your usual columns that are employed in reverse phase LC, C8 and C18. You would also have your column dimension, so you can make use of longer columns or columns with smaller diameters. You also have particle size. Smaller particle size, you can improve the resolution as well. You can increase the number of theoretical plates. But please take note that not all particle size are suitable on your LC system. You will have to check kasi for an HPLC system, your system can only take up to 400 bar of pressure. So usually columns that are used for that type of for this instrument will be up to 3 micron particle size, and as well as certain columns that we will talk a bit later. Now, if you go lower than 3 micron, or if you go below 2 micron, the pressure will increase will be very high. So your LC system might not be able to withstand that high pressure. So in that case, your columns that are smaller than 2 micron yung particle size can only be used for UHPLC instruments. So please take note of that. Particle types, you have different particle types. So you have your polyporous particles, silica particles. You also have your superficially porous or core shell or fused core particles. So this is a bit more, it's a bit newer compared to your fully porous particles. So it makes use of something like this. You have a core shell that is solid, and then you have a porous coating along the surface of that core shell. So the separation is occurring in the surface of the core shell. So in this case, what happens is it allows you to have resolutions that is similar to like those sub 2 micron particle columns, but it doesn't have as much back pressure. So these columns can be used for your normal HPLC systems. So this is just to illustrate actually you can see that the band broadening effect can be reduced by the use of these core shell columns compared to like your fully porous columns. Kasi less na yung pag-permeate niya to the stationary phase. So less na yung band broadening mo coming from that. So you have different types of packing material as well, silica-based. The main advantage is limited pH range. So in some cases, in high or low pH, mainly in very low pH, your silica can actually hydrolyze. So that will damage your column. Now, you also have polymeric columns, more stable for extreme pH, but compared to silica, it's relatively less in terms of performance. You also have monolithic columns that are continuously porous materials. Now, in terms of selection of chromatographic mode, so depended dun sa compounds mo, if you are looking at macromolecules, you mainly use GPC and reverse phase chromatography. Biomolecules, you have a wide selection of different chromatographic modes that you can use. Also still mainly reverse phase. And for me, I also use Helic. Organics that are less than 2,000 daltons or atomic mass units, medium polarity. You would have reverse phase or supercritical fluid, nonpolar, reverse phase, and NARP, NPC normal phase, and super critical fluid as well, and so forth. So you have ions, IEC, IC, Helic, MMCCE. Reverse phase can be used, but normally you might need to use ion suppression or ion pair agents to separate them out. Chiral, you would also have different chromatographic modes available. Preparative is more for like separation for purposes of subsequent collection. You would also have normal phase, reverse phase, supercritical fluid chromatography. As you can see, reverse phase is again very commonly used across the different chromatographic modes and for different types of samples. Now, these are different reverse phase columns that are employed. So mainly, we make use of C18 column. So it's the most retentive alkyl phase for different types of analytes, a wide variety of analytes. You can have C18 polar embedded. So the separation mechanism is mainly C18, similar to C18, pero you can actually retain some of the polar analytes. Kasi when you make use of just C18, yung mga highly polar analytes mo, sasama lang siya doon sa mobile phase, hindi siya mariretain. So for you to have a bit of retention of your polar analytes, then you can make use of the C18 polar embedded. And usually they would have higher stability in full water. Kasi most columns cannot take full water or 100% water. So you would usually need to leave at least 5% organic solvent in your system, in your column. Pero ito, yung mga C18 polar embedded, usually they are a bit more stable. They are more stable in aqueous medium. And yun nga, they can separate out your polar molecules. Not a replacement for hydrophilic or normal phase, but at least it can provide you with a bit of separation. You also have cyanopropyl for polar analytes and solutes with different chemistries. Phenyl or diphenyl for aromatic and moderately polar compounds. Pentafluorophenyl for halogenated, polar, and isomeric compounds. And aminopropyl, it will be a weak ion exchange that can be used with pH control. So this can also be used some for Helic purposes. But in the case of reverse phase, with pH control, it will act as a weak ion exchanger. Now, earlier we've talked about the effect of particle size or changing your particle size to improve your resolution. So you can just imagine your column that is packed with larger particle size particles, and you have those that are of smaller particle size. So you can see that you will actually have an increase in number of theoretical plates. You have sharper peaks. You have better resolution. But you can also just imagine that with smaller particle size, your columns will become more packed. Mas magiging packed siya as compared to having your large particle size particles. So what will happen is you would have an increase in the pressure when your mobile phase flows through the column. Kasi nga, mas packed siya, mas mataas yung resistance ng mobile phase, mas mahirap for the mobile phase to go through the column. So, yun yung disadvantage of using smaller particle size. Now, you can see from here, when you use smaller particle size, you have better, a wider range of linear velocity that is wherein you have the highest efficiency. So you have better efficiency for a wider range of linear velocity compared to when you're using a 5 micron or a 3.5 micron particle size columns. So nandun yung dilemma natin. You can separate better using smaller particle size, less than 2 micron particle size, pero yung back pressure may issue tayo. So subsequently, they developed UHPLC, or ultra high pressure liquid chromatography. So this is one of the most important developments in modern HPLC. This is pioneered by these guys, James Jorgensen and Milton Lee. So UPLC was first commercialized in 2004 by Waters. It allows for faster and better resolution separations. It makes use of particles that are 1.7 to 1.8 micron or sub 2 micron particle size for the stationary phase. So this is just a proof of concept that was done by Jorgensen before. They used capillary column packed with 1.5 micron, and they can get 100,000s of resolution, or 100,000s of theoretical plates for the separation of your different components. So now what we usually have will be in this range of particle size. So advantage of using the flow rate first. The flow rate for making use of HPLC and UHPLC. So the typical flow rates for HPLC will be 0.1 to 10. The pressure limits will be at around 400 bar. When you're using intermediate UHPLC, you can use up to 5 mil per minute. The pressure will be around 600 to 800 bar. And UHPLC, you can use up to 5 mils per minute. And the pressure limit will be around 1,000 to 1,500 bar. So usually for what I'm doing in terms of like sub 2 micron particle size columns, the pressure will be around 400 to 600 bar, which is very close to the limits of your HPLC. So you cannot go too close as well to your pressure limits. Kaya dapat at least if you're using sub 2 micron particle size columns, at least intermediate UHPLC na yung system mo. Now, the benefits of UHPLC, you would have increase in speed, resolution, and ayun. So this is just to illustrate. You have a 2.1 by 150 millimeter column with 5 micron HPLC. The resolution of these two compounds will be 4.6. Now, if you make use of a 2.1 by 30 micron using a 1.7 micron particle size, you have a separation of 2.9, not as good as the one here, pero kasi di ba, requirement natin for resolution is at least 1.5. So actually, you already get enough resolution with just the use of a 30 millimeter column. So super iksi niya. If you increase it to 2.1 by 50, you already have the same resolution with the 150 micron 150 millimeter column. So you can just imagine trying to separate in a 150 millimeter column and a 50 millimeter column. As you can see, from 20 minutes, you can reduce the chromatographic separation to 2.5 minutes. So same resolution, better speed. If you make use of a 100 millimeter column, 1.7 microns particle size, higher na yung resolution mo, And still, you also have much improvement in terms of like your detention time, like the time that it takes for you to do the chromatographic separation. So 4 times yung decrease nung retention, nung chromatographic separation mo. If you have 150 same length but different particle size, your resolution is almost, well, close to double. And you have also an increase in the speed. So drastic increase in speed as well. Now you have 7 minutes for your chromatographic separation. So you can see that there's much to be gained when you're using HPLC. But again, you have to check whether your system is suitable for it. Now, another saving or another advantage of using HPLC, because you have shorter chromatographic separation times, then you would use less solvent. So malaking saving siya in terms of solvent kasi alam natin mahal din ang solvents, and it's more environmentally friendly kasi nga less yung wastage mo ng solvents. In terms of mobile phase composition, this is again something that you can modify in terms of increasing your selectivity. You need to consider the characteristics of good mobile phase solvents. So good solubility, of course, of your sample components, non-corrosive to your HPLC system. Again, as I've mentioned, in some cases, some solvents might not be compatible with your LC system. So you need to check. So yung common solvents like methanol, acetonitrile, water, definitely for all LC systems, for most LC systems, which are usually reverse phase LC systems, they should be okay. But if you're going to start using THF, DMF, or hexane, then you would need to check the materials that are present in your LC system. Of course, you would need high purity to ensure that you don't have high background and ghost peaks that are appearing in your chromatography. Low cost, kasi mahal din ang mga solvents, especially if you're doing preparative HPLC. You would need like relatively large amounts of solvents, then low cost is important. UV transparency, if you're using UV detection, then you would need this. Low viscosity, toxicity, and non-flammability would also be in terms of low viscosity is more for the separation kasi higher viscosity, you would also have more peak broadening. So actually, low viscosity, you would have also better separation. Mas mabilis lumabas yung mga peaks. Toxicity and non-flammability will be more of your safety considerations. Solvent strength. So this will be the ability of your solvent to elute your solutes from the column. So it depends on your analytes as well as your stationary phase. It will mainly depend on your analytes. So ano ba yung mga solvents that will allow you to elute your solutes from your column. So it's related to the polarity. And you would also have your solvent selectivity. So different solvent selectivity will have different solvents will have different selectivity. So solvent strength, for example, if you're making use of different compositions of your ACN, for example, for this two compounds at 100% ACN, wala siya separation. If you decrease the percent ACN, you would have like some separations, and you would have optimal separation actually at 30 or 20% ACN. Now, for solvent selectivity, if you're going to look at the selectivity of methanol and ACN, so again, they would have different selectivities for different types of compounds. In this case, comparing 60% ACN and methanol, these two compounds would have better separation with methanol compared to your ACN. Dito naman, actually, well separated yung 2 sa 20% ACN and 20% methanol, but you have to take note of the time that it takes for the compounds to elute at 20% methanol. So it's around 120 minutes or 2 hours na. Whereas you can use ACN at 20%, it will elute at around 30 minutes lang. So mobile phase composition, usually you would add modifiers to modify your pH and buffers. The pH of the aqueous mobile phase can actually have a dramatic effect on the retention of ionizable analytes. So especially if you're doing reverse phase LC, you would want your components to be in the neutral form, in the non-ionized form, for it to have better retention on your stationary phase. Kasi kapag ionic na siya, less na yung magiging interaction with the stationary phase, then it will elute out too early. So you would need to modify the pH to make your compounds in the neutral or non-ionized form. So yun, ito yung part na yun. Now, you can use different buffers, acidic or basic modifiers to control your pH. You have to consider their UV transparency. You would want to use those that have less or have less absorption in UV. Kasi usually your detection will be at around 220 nanometers onwards. So you would want your buffers to have a UV cutoff of less than that. Now, another consideration for MS applications, when you have mass spectrometer for your detector, then you would need one that you would need modifiers that are volatile, kasi you evaporate off those mobile phase components before ionizing your analytes. So you would need to make sure that your additives, such as your buffers or acids or bases, are volatile. Elution program, so you can have either isocratic elution or gradient elution. So isocratic versus gradient elution. So in isocratic elution, you have a constant mobile phase composition throughout the run. So for example, if you're separating with isocratic, you can fix your mobile phase composition at 50% of ACN and water. For gradient elution, the mobile phase composition changes through time. So this is more commonly used in reverse phase LC, especially if you're looking at a lot of different components. If you can see here in the isocratic, you have sharp peaks that are in front, not that well separated, especially as you can see here, you have some overlap between B and C, and you have F that is coming out much later, but it has a very broad peak. So alam naman natin that those that are coming out much later are those that are being retained in the column more. Now, if you have the same mobile phase composition, actually it will be harder for those that are strongly retained in the column to come out, and so mas nagiging wide na yung peak as time goes. Now, if you use gradient elution, as you change the mobile phase composition through time, then you will be able to better separate out the different components at the start through changing your mobile phase composition, as well as get those that are strongly retained to elute out earlier, as well as with a narrower peak. Kasi you can increase the concentration of your organic mobile phase at a higher concentration, then it will allow the elution of those that are more strongly retained in your stationary phase. So makita nyo yung difference between isocratic and gradient elution. Okay, now let's go to the detector. So this is a very important part as well. Aside from the chromatographic components, your stationary phase as well as your mobile phase, importante rin yung detector. Otherwise, wala tayong makikita. So, for detector, usually, if you have chromophore containing analytes, the most commonly used detector will be UVVs or diode array detector. So, detection is set at the maximum absorption wavelength, or if you are screening for a few compounds or many compounds, you might need to compromise. Kasi syempre, in some cases, you might only have a UVVs detector, so it can only have a few wavelengths. In that case, you would need to select wavelengths that can detect most of the compounds. Like if you can have like 2 or 3 wavelength that can detect all compounds, it might not necessarily be at the maximum absorbance wavelength, but it should allow you to detect all. So in some cases, you might need to compromise, but as much as possible, detection should be at the maximum absorbance wavelength. Now, if you're using a diode array detector, you can actually scan through the whole range of wavelength, through a whole range of wavelength. So in that case, you can generate something like this, a three-dimensional data wherein you have separation through time, then you have different detection wavelengths, and then you have the intensities. So as you can see, para siyang you have further separation. In some cases, if you have components that are eluting at the same time, you might be able to differentiate them based on the um, detection wavelength that you are going to use. So in this case, if you're scanning a whole range, you can actually separate those that are eluting very close to each other or overlap. Now, if you do not have chromophores, so ang chromophore kasi, if you have analytes, as you can see from here, you have alternating double bonds. So these alternating double bonds are what is called conjugation. So if you have highly conjugated systems, you can absorb more in the UVV's region, then sila yung may absorption at UVV's wavelengths. Now, if you do not have chromophores, this conjugation, then it will be hard to detect, or they are not detectable using your UVV's detectors. So what you can do is you can derivatize, you can add a chromophore to your compound, or you can make use of other detectors such as refractive index detector, which is a universal detector, evaporative light scattering detector, charge aerosol, fluorescence, and mass spectrometer, or tandem mass spectrometer. So mass spectrometer, a tandem mass spectrometer only for ionizable species. So detectors, you would have different detection limits. So UV absorption will be mainly from 1 picogram to 1 nanogram. Not relatively sensitive, not very selective. It can be used for direct, indirect approach. Fluorescence, you have higher detection limits. But again, it's either your compound would need to have natural fluorescence, or you would need to do derivatization. Refractive index detector will be a generic detector, a universal detector, kasi it can detect any components as long as there is a change in refractive index versus your reference. So it's not selective and relatively sensitive. You also have electrochemical methods, FTIR, that can be used for structural elucidation, and you have your mass spectrometer that can have detection limits of 100 attogram to 1 nanogram, and then you have, since it's highly sensitive, it can be used for structural determination and can be highly selective in tandem MS mode. Now, for me, I mainly use LCMS, so I'll discuss a bit more on this aspect. So this one is very useful for both qualitative and quantitative analysis. It can be used for identification of compounds. It can be used for highly selective detection. So compared to hyphenation with other detectors, it can provide higher sensitivity, higher specificity, and more definitive information on mass and structure. So it can be used to analyze a diverse range of non-volatile compounds, including those of high molecular weights and polarities. But you have to consider a very important consideration is it can only analyze, or it can only detect ionizable compounds. So if your compound cannot ionize, then it cannot be detected using MS. So you need to ionize compounds. You need to ionize your compounds either through the addition of mobile phase modifiers to make it like protonated or deprotonated, or it can be through like certain ionization modes. In gas chromatography, you have electron ionization. You fragment your ions, you fragment your analytes, creating your ions. You can derivatize and so forth. So that will be for LCMS. Components will be, of course, you have an HPLC or UHPLC in front. You have a mass spectrometer. Your ion source will generate your ions. Then you have your mass analyzers. So different mass analyzers will have different functions. There are those that are filtering. So like quadrupole, they can filter off certain mass range. So, or it can select, it can detect, it can choose to detect only selected mass range. And then you have those that are sorting. So sorting, they are usually high resolution instruments, or MS, that allows you to scan your ions and separate them out, and give you high resolution mass spectra. So with that, you can actually identify compounds based on the based on the accurate mass that you get from the mass spectrometer. And you have your detector. So you have the mass analyzer to filter out or sort your ions. Then detection will be at your detector. Then you would also have your instrument control and data system. Now, as I've mentioned, similar to for MS, for mass spectrometer, you actually have an additional dimension of components resolution. So similar to your DAD detection, this one you have a separation based on chromatographic separation. You also have separation or resolution based on the wavelength. Similarly, in this case, you would have chromatographic separation as well as resolution based on your mass to charge ratio. So that is the advantage of your mass spectrometer. Now, LCMS and LC can also be coupled with NMR. This one will be a bit more relatively newer. Now it's very useful for natural products analysis. LC will be coupled to your NMR and mass spectrometer. So dapat parallel. Hindi siya pwedeng serial. Well, actually, pwede siyang serial. So for you need to have your NMR first before your MS. So in this case, you have a chromatographic system. Then you have an initial LC detector, either a UVVs, RID, or whatever. Then you have an NMR detection cell. So from there, you will be able to directly submit your peaks for detection using NMR, and then you will be able to generate your NMR spectra for structural elucidation. Now, NMR is non-destructive, mass spectrometer is destructive. So if ever you're going to couple them together, it's usually LC, LC detector, NMR, and then mass spectrometer. But in these cases, in these setups, it's mainly parallel. So you have a split of your elution towards your NMR and towards your mass spectrometer. So applications of liquid chromatography in natural products research, you can look at it in terms of, well, first, natural products, sorry. In terms of natural products, we talk of products of natural origin. So they can come from plant, animals, or microorganisms that have not gone through any processing or treatment. It can come from parts of an organism, or it can be extracts of an organism, parts of an organism, or exudates. This can also refer to pure compounds like lignins, anthocyanins, coumarins, etc. Now, when we talk about natural products, they usually refer to the secondary metabolites. So these secondary metabolites are small molecules that are less than 2,000 AMU molecular weight. So actually, all compounds that are coming from natural origin are considered natural products, pero usually for drug discovery purposes, ang focus is on the secondary metabolites. So these small molecules. They are not necessary for growth, reproduction, development, or survival of the organisms, and they are usually produced due to nutrient limitation, idiophase, defense mechanism, or metabolism regulation. So they are usually produced under stress conditions or defense mechanisms. Some examples of drugs that are derived from natural products will be Taxol from the bark of Taxus brevifolia. You have these vitamins that are derived from your cod liver oil, and you also have penicillin that is extracted from Penicillium notatum. So these are just some examples of drugs or components or vitamins that are derived from natural products. Now, natural products are very diverse. You have those, a lot are coming from your plants. You also have those that are coming from bacteria, fungi, as well as from certain animals. Now, natural products research in the Philippines is very much it's very diverse, and it's a very hot topic. This is because we have a rich biodiversity of natural products in the country, and it is actually one of the priority area in the National Unified Health Research Agenda. And of course, I'm sure you're familiar with the Tuklas Lunas program of DOST, PCHRD, and you have different centers across the country that is engaging in natural products research. Some successful commercialized products will be your Lagundi for cough and asthma, Sambong for kidney problems, anti-urolithiasis, and diuretic. And this is for treatment of kidney stones. And you have your tawa-tawa, which is used for the treatment of dengue. So when we do LC for natural products, or even for other types of samples, we need to consider what is our goal. And then from there, we will be able to determine ano ba yung dapat na gamitin natin na type of HPLC. So first, if you want to determine the concentration of your analytes, then you would need to do quantitative HPLC. So in quantitative HPLC, you optimize the method for a specific group of target. You use calibration standards for absolute quantitation. Now, if you just want to confirm the presence or absence of analytes, profile the sample or fingerprint the sample, this is mainly to like create something that is identifiable to that type of sample, or if you just want to detect the presence or absence of certain compounds, then you would have an HPLC method that is known to be qualitative. So that one, again, mainly for identification, and it's exploratory. Method optimization is usually to detect more compounds, not specific to a certain target compound or group of target compounds. And you can do both, either absolute or relative quantitation. Lastly, you would have, if you want to isolate components for further work, then you would want to do preparative HPLC. So in preparative HPLC, the method may be optimized to ensure the separation of the target compounds from other components of your mixture, and you can collect them, these separated components, for further isolation, for further fractionation, or for characterization. So first, preparative HPLC. When we look at natural products drug discovery, you have different steps. So first, you have an initial screening. You have multiple plant materials. You can do small scale or micro extraction. You subject them to bioassays, and then you obtain the active. So from there, you will be able to determine the active plant extracts. Now, if you do, from there, you will be able to isolate and identify active molecules. So from the active plant material, you do some initial preparations, you grind them, you do large scale extraction. From there, you can do bioassays. You do preliminary fractionation using either chromatography or solvent partitioning. So in solvent partitioning, you make use of different solvents of different polarities to separate out different components of your sample. So you can separate out your nonpolar components in, let's say, for example, in dichloromethane or chloroform or hexane, then your polar components in ethyl acetate or methanol, and so forth. Now, these can also be subjected to bioassays, and then you can again do chromatographic analysis and further fractionations, subject it again to bioassays. Once you have chromatographic, subsequently, you can still do chromatographic purification of active fractions, and then you can subject the compounds to structural elucidation. Once you have the fully characterized compounds, then you can proceed with drug development. So this one will be more for the pharmaceutical side na. Now, different, before we go through the preparative HPLC, just a brief explanation of the extraction procedure. So you would need to involve some solid liquid extraction, some initial sample preparation. So these are the different steps that you need to do. Wash the samples, dry them, either air drying or freeze drying. If you want to analyze, well, for GC, if you want to analyze volatile compounds, please do not apply drying procedures that will allow the volatile components to escape. So you would need to consider that. Size reduction will involve winding and milling to increase the surface area that's exposed to your solvent. These are the equipments that you are going to use. This ensures sample homogeneity, greater surface area. So this is a freeze dryer for freeze drying. Facilitate entry of solvent and storage. Now, you need to ensure that you store your samples in a cool and dry container. You need to ensure that you keep them in good condition before you subject them for analysis, of course. So solvent extraction, you have different stages. Solvent presentation of the sample matrix, dissolution, diffusion of your solutes from the matrix out, and then collection of your extracted solutes. Your considerations will be the properties of your extraction solvent, particle size of the raw materials, solvent to sample ratio, extraction temperature. So in some cases, you might be able to employ heating to increase the extraction and extraction duration. So these are different solvents that you can use. I'll just quickly go through them as we're running out of time. So you need to consider selectivity, low toxicity, of course, for safety reasons, as well as low flammability and risk for explosion, low potential for artifact formation for the LC detection, and economical and environmental friendly. So most will be quite okay to use. Perhaps chloroform, medyo nagka-cut down na tayo on using chloroform because these are chlorinated solvents and they are not as environmentally friendly. If you can extract your samples in methanol, ethanol, water, they are relatively safer. Then they are also easier to use. And of course, you need to consider what would be as exhaustive as much as possible. You want to extract as much of your components as possible. So these are different solvent extraction techniques that you can use. You can do maceration. It can be at room temperature. So basically, you just immerse your samples in the solvent for a few hours or overnight. You also have your percolation, decoction, reflux extraction. You have those that are use less solvents. They are micro extraction techniques, and they make use of less solvents. They are more environmentally friendly, such as your ultrasound assisted extraction, microwave extraction, pulse electric field extraction, and etc. So yeah, this will be perhaps another topic. Okay, so now we go to preparative HPLC. So before, the distinction was based on columns. So we say preparative because they make use of very big columns. Now analytical will be, they make use of analytical columns, which are smaller diameter columns. Now it's based on the function. So of course, analytical LC will be, or HPLC will be for separation of components for purposes of detection. Preparative will be separation of components for detection and subsequent collection for further purification or characterization. So, ang preparative HPLC, it will have the same components as an analytical HPLC, but it will have this fraction collector that will allow you to collect your fractions for further fractionation, isolation, characterization. So these are the different stationary phases that are used. Columns for preparative LC, you have analytical configuration, you have semi-preparative, preparative. So basically, they are different in terms of like the amount of material that you can purify. So smaller amounts for analytical, semi-prep will be up to 640, and preparative will be up to 4,000 milligrams. The column dimensions will be different across the different configurations, as well as the flow rate that is being used. Now, some example of this will be the isolation of formononitine and other phytoestrogens from red clover. So this is just to show you. You have your initial analytical HPLC separation. You have formononitine here. They are separated using a C18 column with 0.1% acetic acid in water, 0.1% acetic acid in acetonitrile using a gradient elution program. Now, this is to show like at different, you can actually increase the amount of the sample volume and consequently the amount of sample introduced to the column. As you increase, at this point, the change in the profile is not so much, but you can already see some peaks are already overlapping. So this, you can see the effect of overloading in this experiment. Subsequently, they did fractionation collection for this red clover extract. Once they have pulled the extracts and they again subjected to analytical HPLC, you can see that you obtain relatively pure compounds already. So you have formononitine extracted, isolated from the other components as well as the other phytoestrogens. You can actually scale this up, so you can make use of a bigger column, 21.2 internal diameter. You can inject 2,300 microliters. So in this case, you have for this initial fractionation, you need to do multiple times, and then you're going to pull the collection from those multiple runs, and then that's what you use for subsequent steps. For if you use a bigger column, you can inject more, and actually you can be able to obtain the same amount of sample in either only one run or in just in a fewer number of runs. Quantitative analysis will be again involving a method that is optimized for certain target analytes. So you make use of calibration standards for absolute quantitation. This is an example of the separation of your anthocyanins using HPLC DAD at 520 nanometer wavelength detection. So this again, quantitative analysis, you have a specific specific targets or target, and then you are after quantitation. Now, qualitative analysis can be used for, again, this is identification exploratory. You optimize the method to detect as much compounds as possible, and it can either allow you to do absolute or relative quantitation. So this can be used for chemical fingerprinting. So yung chromatograph na generate mo can serve as the fingerprint of your sample. So it can be used for purposes of identification, authentication, it can be used to distinguish different species of different strains of a particular species, or it can be used to distinguish the same, for example, plant sample obtained from different parts of the country, or it can be used for like quality control purposes. So just an example, this is a Danshen injection. So Danshen is actually a traditional herbal medicine from China. They did chromatographic fingerprinting using HPLC DAD, and these can be used for quality control purposes. So you can detect batch to batch differences. You can detect differences between different manufacturers and so forth. Now, in natural products discovery, you have highly complex mixtures. Now, you isolate bioactive compounds that sometimes lead to loss of bioactivity. So, alam naman natin, when you have complex mixtures, natural compounds, natural products, they can have like synergistic effects. So that means the effects of certain active compounds can only be there because it has to have certain other components. Now, if you take out that particular component or that compound away from the other components that introduces this synergistic effect, then you can have a loss of bioactivity. So you can have also degradation or chemical modification of the compound during the process, and yun nga yung synergistic effects. So frequent rediscovery of known compounds. So this one, pwede na kasi if you're doing natural products drug discovery, you would want to identify novel compounds, not necessarily those that are already known. And so if you go through the whole process, you might in the end up with the same compounds that are already known. So it kind of wastes your time doing the doing the workflow. So investigation of crude materials is irrelevant to desired bioactivity. So kumbaga you do not find the bioactivity that you want from the materials that you have. Now, in the replication, we have this technique known as the replication. So it involves the use of different combinations of techniques to allow the identification of biologic compound leads or novel compounds. So it is first defined by Butler to quickly identify known chemotypes. So it allows you to identify those that are already known so that you can focus on those that are not yet known. So kumbaga, nagtitriage ka na. Kung sa ospital, you have a triage where you separate those that are, for example, critical, non-critical, those that can be outpatient. In this case, you are separating those that are already known from those that are interesting or something that could be of interest. So it helps reduce timeline for natural products discovery. So there are different replication strategies. Usually, you will make use of DAD or LCMS for these purposes, or even LCNMR. So you can have natural extract, fractionate them, subject them to targeted analysis, and identify based on database. You can also have different fractionations. You subject them to biological tests, analyze only active fractions, and identify them. Or you can do analysis of all fractions, identify from the metabolite database, and do biological tests only on those that are unknown. You can also do natural extracts, subject them to fractionation, and then do targeted analysis. So this is more if you're after specific compounds already. Now for microbial natural products, then it will be more of this workflow wherein you make use of gene sequencing, PCR fingerprinting, or phenotype analysis, do clustering analysis, and subsequently identify, do taxonomic replication based on microbial strain. So this one, not so much our focus, but in terms of LC applications, you can actually apply LC for these different types of the replication strategies. Now, aside from those four, aside from the three that I mentioned that makes use of LC, you also have metabolomics-based replication workflow. So in this workflow, you have natural extracts. You would subject them to a targeted analysis using LCMS, NMR, or GCMS. For now, our interest is LCMS. You subject them to parallel bioactivity assay, do your chemometric analysis, and then from there, identify your metabolites. Now, if you do parallel bioactivity assays, then you'll be able to see in the chemometric analysis, like what are those compounds, or which samples are actually active, which are not active, and consequently also identify the MZ or the ions that are influencing the separation between your active and inactive extracts. So kumbaga, it actually allows you to skip several steps of your natural products drug discovery, in the sense that you don't have to go through so much fractionations and do so much bioassays to identify kung ano ba yung mga compounds of interest. So it can be used for high throughput profiling of natural extracts. It allows you for the quick identification of compounds from crude extracts. So it can allow you to identify compounds, again, based on high resolution, based on accurate mass and MSMS fragmentation data. You can compare it with databases and allow the quick identification of your compounds. And you can also do molecular networking to, for those that are not known, you might be able to see them in the same network as those that are already known. Then you'll be able to also do structural elucidation based on that information. Now, this is an example of metabolomic-based replication. So you have these British bluebells. They subjected different parts of this plant to extraction and subsequently to LCMS analysis. And then from there, they were able to find separation of the different chemical profiles or metabolic profiles of your bulb from the aerial parts. And from there, they identified that actually the bulb will be containing more of your low molecular weight compounds. Around here, it's around 400 plus Dalton. The aerial parts will be those that are containing higher molecular weight compounds, around 1,000 plus Daltons. And here in the bulb part, there's actually two ions that are differentiating. I think it's 483 and 455. So actually, they can be found in the same molecular network, and this actually indicates that they are coming from the same class or family of compounds. They also did OPLSDA to further separate out the different plant parts. So as you can see, you have your leaf, shoot, your scape, and flower separated out. And from there, you'll be able to identify which ions, and so consequently from which ions are differentiating your leaf, those that are higher in your leaf, in your shoot, in your scape, in your flower. And you can also identify them based on accurate mass as well as MSMS data. They also, so this part, they are looking at anti-trypanosomal activity. So they wanted to see which fractions actually have anti-trypanosomal or trypanosomal activity. So trypanosoma is actually a parasite that can cause trypanosomiasis. So from here, you can see differentiation of your active and inactive components. And from the OPLSDA plot of these active and inactive components, you will identify those that are active and those that are inactive. So those that are found earlier, yung 455 and 470, they are identified, but they are found to be not contributing to the activity, to the anti-trypanosomal activity. Instead, you have this compound that is 1283 that they identified to be silanoside L1. That is one of those that are contributing to the active or to the activity of your extract. So they were able to identify these. They looked at the molecular network. They found this other compound, which they subsequently structure elucidate, and they come up with the saponin glycoside of saponin glycoside compound. So actually, this saponin glycoside compound was found to have anti-trypanosomal activity of 98.9% at 20 micromolar concentration. So here you can see different applications of natural products. You were able to obtain a background on the different considerations that you need when you're performing HPLC. Now we have several HPLC instruments at CIF. So we have an analytical HPLC that can also be used for GPC or gel permeation chromatography, having multiple detector system. We have a UV variable wavelength detector, so it can detect two wavelengths at the UV region. We have refractive index detector as well as light scattering and viscometry for the GPC. So for GPC, we can do molecular weight distribution analysis for your polymers. So semi-preparative HPLC will again allow you to fractionate and collect your extracts, fractions of your extracts for subsequent fractionation, isolation, or purification, for characterization, or for your bioassays. You also have your UHPLC cutoff for quantitative analysis, as well as for high sensitivity and metabolomic analysis. So for your analytical requirements, we have different labs available in CIF, different types of instrumentation. You just email us. And again, we also have other equipments in the facility. So that's all for this presentation. Thank you very much for your attention, and thank you for spending your Saturday with us.
And thank you, Dr. Karen Laserna, for your very comprehensive discussion on liquid chromatography. So hindi po natin makukuha anywhere yung level of detail na binigay po ni Ma'am Karen, ni Doc Karen dito sa we covered the basics and ended up with the very sophisticated applications of LC. And but before we entertain any question, I will just give some breather to Doc Karen, a little water break para po makapahinga naman na konti yung lalamunan niya.
Sige, sige.
That was 2 hours straight talk, so I couldn't really imagine this ride. Ito po, konting break lang po muna.
We are also proud to share that Filipino Science Hub is now a registered non-profit organization in the United States of America. We have big STEM education problems to solve, but in 2022, expect a bigger Filipino Science Hub.
Alright. So indeed po talaga 2021 was a big year for Filipino Science Hub. And yeah, we had a lot of milestones. We had indeed reached a lot of milestones in 2021, and we're all excited for this year. We're getting bigger, and as Doc Jeff mentioned, we are now a registered nonprofit in the US. So there are always exciting things to happen, and we're looking forward to a more productive year here at PhilSci Hub. So now we're going to entertain some questions. So we're just going to keep it short because we're running out of time.
Sorry, napahaba uli yung talk.
Oo, Karen, sobrang para siyang crash course sa liquid chromatography with para siyang crash course reloaded, parang gano'n. Sobrang informative and information packed. Ayan, so ito yung mga questions. So let's start with a question from Zoom from Daniel Day Medina. Paano po ba malalaman kung ano ang preferred chromatography, chromatographic method siguro, ang gagamitin for the sample? So, ayun po. Yan ang question niya.
Yun. So, actually, depende siya sa, well, it depends on your purpose as well as for your, depends on the analytes na gusto mong i-detect. So, kasi you would depend on the polarity of your molecules first. So, yun. You would need to consider kapag yung polarity ng molecules mo, if you're doing LC, for relatively non-polar molecules, then you would do reverse phase. For polar molecules, then you would do either ion exchange, hydrophilic, or normal phase. You would also need to consider ano ba yung gusto kong gawin? Do I want to detect all that I can detect, or do I want to just detect a specific group of compounds? If you want to detect as much as possible, then you would usually go first for reverse phase, C18 column, kasi mas applicable siya to a wider variety of compounds. Then, if you want to do more targeted analysis, for example, if you're specifically looking at aromatic compounds, then you might want to consider, aside from reverse phase, you can also do, you can use phenyl or diphenyl columns for that. And yun nga, so yun, depende sa compounds, depende sa samples.
Mm-hmm. Depende sa purpose.
Sa purpose, sorry.
So talagang dapat we do our background research first,
Yes,
no? Before we even consider picking out the chromatographic method for our samples.
And yun, kung wala ka mang initial background on your sample, kung ano yung contents nun, then just go for something that is a bit more generic nga. So just go for exploratory muna, then do your reverse phase C18 analysis.
Okay. So next question from Dominador Calio, also from Zoom. Hello po, Doc. Ask ko po why we are using matrix for some analytes. What is its purpose? Thank you po.
Actually, yung matrix is actually, they are present in your sample. So when you do extraction, hindi lang yung mga analytes yung na-extract mo. Sumasama dyan yung ibang contents nung sample mo. In some cases, yung mga lipids, yung tannins, or chlorophyll, sumasama yon. So they are the ones that consists of your matrix. Now, if you, kumbaga, kung ano yung mga contents of your sample that is aside from your analyte, that is considered your matrix. So if you look at seawater, then of course you would have your analytes plus yung matrix that is coming from your seawater, and yun yung matrix na sinasabi. So they are naturally present in your sample. It's not something that you add in.
Mm-hmm. At yun nga po, sa matrix, we have as little interference as possible. So very important po yung sample prep.
So you would want to remove as much of the matrix as possible. So you can do that by being selective in the solvent, as well as through sample cleanup, like using solid phase extraction. So yun.
Yep. Okay, from Robert Riggs Rondilia, from YouTube. Good morning, Dr. Laserna. In LC-NMR, does LC solvents need to be removed first before subjecting to the NMR analysis?
Yes. So usually they would have like so in between the LC and the NMR, they will have a trap. So dun sa trap na yon, it will try to trap the analytes of interest, let the other components elute out, and then subsequently dun sa trap i-introduce yung deuterated solvent para yun yung pupunta sa NMR.
Okay. Hindi pa ako nakapag LC-NMR so
hindi pa ako. Ako rin, hindi pa rin.
Okay. So ito naman, generic question lang. How do we determine the correct mobile phase for HPLC experiment? So I think na-touch na ni Doc Karen to early on. So
related din yun.
Yeah.
So depende dun sa chromatographic mode mo, this will depend on your sample, your purpose, your analytes.
Yep. Okay. So how often should I backflush a column? So ginagawa natin ito para linisin, di ba? Yung column.
Actually, if you're just going to clean it for regular cleaning, you don't need to backflash. Ang backflash, ginagamit lang siya to remove yung mga clogging. So kapag nakita mo na tumataas na yung pressure ng column mo, kasi usually you have to monitor the column pressure per run every time na ginagamit mo siya. Kapag nakita mo trending na tumataas na yung pressure, then you might need to do further cleaning. In some cases, you might need to backflash the column. Now, not all columns can be backflashed. So there are columns that can be backflashed. There are some that cannot be backflashed. So you need to check the column manual to see whether it can be backflashed. Kung hindi, then better not. Yun.
Yeah. That's the rule. Don't fix it if it's not broken. Okay. When should I use a guard column?
Yung guard column, well, as much as possible, if you can afford to buy a guard column, then it will be better kasi it will help protect your main column, your analytical column. So it can protect from some impurities, from particles, particulates, and other contaminants. So yun, as much as possible, if you can afford, then please go ahead, make use of a guard column.
Just for the sake of those who are not aware of guard column, ito po yung parang column na nilalagay po natin just before the column, no? Sa HPLC natin para filter out any impurities in our sample.
Usually, it will contain like stationary phase material similar to your actual column. So if you're using C18 column, then you would have a corresponding C18 guard column for that. So, yun, para hindi rin siya maka-apekto sa chromatographic separation mo.
Yep. Okay. So from Jason Alpano, I think Jason is present here in Zoom. So Jason, would you like to ask your question live? Kasi Jason is also an intern at PhilSci Hub, and he's essential actually. Jason, are you here? I can just ask. Hello, Dr. Laserna. Nice talk. I have read that compound annotation is still a bottleneck process in natural products using LCMS. How do you usually annotate features in your spectra aside from proprietary databases? Specifically, the use of GNPS po for compound mass spectral matching. Paano po ba ginagawa yung molecular networking? Thank you.
So medyo mahaba-habang workflow to. Pero sige, let's just briefly. So initially, again, for me, in terms of like mass spectrometer to use for identification, you need to use high resolution, high accurate mass spectrometers. So QTOF, Orbitrap, FTICR, magnetic sector. So number one yon. You cannot do these identifications based on quadrupole MS scan. So dapat high resolution MS muna, yun yung gagamitin mo. Then you can do annotation, as you mentioned, from proprietary databases. You have your Metlin, HMDB. They would have like some capabilities to allow you to enter your accurate mass as well as your MS ions, and then you'll be able to identify from there. Yung GNPS, ayun. So as you mentioned, not all compounds, specifically those that are coming from natural products, are present in these databases. Kasi yung mga database na to, they are mainly for human metabolites, for pharmaceutical compounds, toxicants, yung mga yun. Now, for natural products, as we know, it's very diverse. There's so much natural products. Marami pa rin hindi alam. So, you make use of, you can try to identify some of them using the databases because some are already published in literature. But for those that are not identified, as I've shown in the example earlier, you can do molecular networks, molecular networking. So dito na papasok yung GNPS. So what GNPS does is it makes use of your MS data. So again, first requirement, it has to be high resolution MS. Second is it has to be able to do MSMS or MSMS acquisition. So from the MSMS data, from the fragmentation data, it will try to create molecular networks for those that have similar fragmentation patterns. So assuming that they have similar fragmentation patterns, nandun na yung papasok yung assumption that they are coming from the same class of compounds, or they would have similar moieties present in the structure. So doon papasok yung molecular networking. So once they are in the same molecular network, you can already have like some idea that, okay, they're coming from the same molecular compound, then you would just need to interpret the mass spectra. So hindi pa rin madali yon. So still, it's still a bottleneck, but you have this molecular networking that can still help or facilitate faster identification. So ganun yung molecular networking. So what you do, you acquire high resolution MS and MSMS data. You convert the data to the format that GNPS requires. So I think GNPS requires MZML format. And then from there, you upload, and then it will do the molecular networking. So after nun, interpretation, bahala ka na rin dun. It will just show you the networks. And it will show you the networks plus some identifications based on what is already available in their database. So kaya they're also advocating uploading of datasets, kasi as you upload datasets and meron ka mga identifications for those datasets, that can actually help the community, the wider community, to be able to annotate yung ibang data nila. So yun.
Okay, so it's really an expanding body of knowledge, no? Okay. I have here a question from Zoom, maybe just last one, from John Paul Ramos. Hello, Dr. Laserna. Would the 2DLC be able to use different columns in the analysis of the same sample? Would 2DLC be using the same detector, or would it be possible to use different detectors as well? Thank you po.
Okay. So yung 2DLC, you can actually use either same chromatographic, same column chemistries, or they can be separate. Or they can be different column chemistries. So for example, if you're using reverse phase LC sa front, then you can use Helix as a second station column chemistry. So you first separate them based on yung relatively nonpolar, and then you can separate them based on hydrophilic interaction subsequently. So you can do same column chemistries. They can be of different column chemistries. They can be of different chromatographic modes. So different combinations can be used. Now, ngayon, ano yung isang tanong? If they can be used, if they can have different detectors, usually they would have a detector after the first chromatography, so that mapipili mo kung anong gusto mong i-fractionate. So you have that option. From based on the retention time, you'll be able to pick which ones do you want to fractionate in the second dimension. In some cases naman, I think as long as yung detector mo is non-destructive, it can be used for the first and second dimensions. Kasi of course, in the first dimension, ayaw mo naman na mawala na kagad yung analytes mo. So definitely MS is out of the picture. You can use UV, VWD, DAD, RID, or others, but usually it's either UVVs na ginagamit sa simula. So first dimension, then a detector, then the next one, second dimension of detection, second dimension of LC, then another detector. So ganun usually yung ginagawa sa 2DLC.
Okay. So ayun, that's all the questions I have. Meron pang pahabol dito si Miss Arian Letada. Is there a chance po that you can conduct actual demo on the use of HPLC? Punta po kayo sa CIF.
Pag hindi na masyadong restricted. Naka-ano kami ngayon, naka-work from home. So, once less na yung restrictions, we will be open to conducting face-to-face training. So hopefully soon.
Yeah. That's all the questions I have. So at this point, magpapasalamat na po tayo sa ating speaker for today, Dr. Ana Karen Laserna. It has been a very comprehensive discussion this morning. Maraming salamat again, Karen, Doc Karen, sa time and sa effort po. Sabi nga, talaga nakarampa siya, pero kita niyo naman yung level of detail na binigay ni Doc Karen sa atin. At this is very instructive po sa mga college students na nag-aaral ng analytical chemistry, and also sa mga high school students po natin na touch ni Doc Karen yung mga simple LC techniques like PLC na pwede natin gawin sa bahay, even for sa ang naalala ko lang yung yung pen ink, tapos pwede natin gamitin yung alcohol just to illustrate the concept to our students. So ayan po. I-share ko na po ngayon yung link for the certificate.
JP, can I just add for a very short moment lang? So yun, if you want to submit samples for analysis, it would be useful for us if you would have some initial idea na kung ano ba yung gusto nyong gawin. Do you want to do untargeted or targeted? Do you want quantitative or exploratory? Or if do you want to analyze specific compounds? So if you would be able to provide that initial information, then we will be able to determine kung ano ba yung pinaka-suitable na method para sa inyo. So yun, I hope this will help you to identify that for your research.
Yes. So you can probably just send them an email even before planning to bring the samples, no? So kung sa literature review nyo pa lang, pwede nyo na silang tanungin kung ano yung pwedeng gamitin na method. Okay. So ayan po, I've already shared the link for the certificate. So I hope everybody gets the chance to fill up the form. Kasi yan po yung gagamitin natin for the issuance of your certificates. And please allow us 7 days to complete the issuance. So kasi by batches po ang issuance natin. And you can send us an email if you haven't received your certificates after 7 days. So ayan, we're right on time. Again, we would like to thank everyone who joined us here on Zoom. So, yung limit po namin sa Zoom ay back to 100 kasi nagtitipid po kami. Joke na. Ayun po. But we're always streaming this live on YouTube. And if you missed anything on the discussion, you can always go back to the recorded video. And yung mga colleagues po natin na hindi naka-participate today can always go back to the recording on our website. So posted na po yan, and they can also avail of the certificates by watching the recorded webinar. So ayun po. Again, thank you very much for this very productive morning. Thank you, Doc Karen. Thank you to the team. And we'll see you again next time. So we will just post our announcements on our Facebook page dun po sa mga succeeding or subsequent namin na mga offerings for webinars kasi finifigure out pa po namin yung scheduling for this for this time. Okay? So we'll see you again. Please follow us on Facebook, our YouTube channels, and all of our social media handles. And check out our website at www.philscihub.com. And ayun, magsama-sama po tayo ulit to learn and learn together here at the Filipino Science Hub. Thank you very much. Thank you, Doc Karen. I think we will have
a good weekend, everyone. Ingat kayo.
Yep.
Ingat tayo lahat.
Mm-hmm.
Samahan po niyo ako sa pagbabalik sa isang taon ng Filipino Science Hub.
Okay, I will stop. I will end the meeting at this point. So thank you very much po to our Zoom participants. Doc Karen, we will have